Okay, so pH curves is the theme. I'm going to start with the review part. I'm going to do a pH curve for a strong acid with a strong base. Now, just like in Chem 20, we always see this wording with the titrated with between our two chemicals. What comes after the titrated with is our titrant. So if you're not quite fully picturing this, if you remember from Chem 20, if you have a burette, okay, and then down below you have an Erlenmeyer flask. These are very crude sketches. The sample is what is down below in a titration, and up in the burette is your titrant. So in this example, we have a strong acid down here as our sample. We end up in our titrant. We're not sure what it is. We have a strong base, okay? Something like sodium hydroxide or calcium hydroxide. Okay? And last year we just did quantitative reactions. This word means 100%, and it's going to come up again throughout this lesson. Okay? Now a specific example of a strong acid with a strong base would be hydrochloric acid titrated with sodium hydroxide. Okay, so we're starting with the acid, we're starting acidic, and we're going to be adding a strong base to it. We could run through the 5 steps to predict our reaction. If we do that, a strong acid is something we have to break up. We don't leave together. We break up HCl because none of it stays together. Okay? Strong means 100% of the H separates from the Cl. So when I build my list for the 5 steps from a few lessons ago, I'd include hydronium. That's how we express that H+. Okay? Instead of just H+, we add it to a water. And we have chloride ions. Moving along, we have an ionic compound, so we're going to break that up. It's also a strong base, so another reason to break it up. And so that gives us sodium ions and hydroxide ions. I'm not going to do all the labeling, but we have the strongest possible species in our table, the gray line on the acid column. That's going to be our strongest acid, and as soon as we see hydroxide, hopefully we don't even look at our table. That's our the strongest base. So when you have a strong acid reacting with a strong base, the Bronsted-Lowry chemistry that you get is hydronium reacting with hydroxide, and you get 2 waters with this H+ transfer. What this reaction looks like in terms of a pH curve. I'll talk about the axis and then I'll do the shape. So the volume of titrant is always our x-axis. Okay? It doesn't have to be in milliliters, but that's the most common unit you'll see. The responding variable on the y-axis is pH. Okay? That's what changes depending on how much titrant is dumped in. We don't have any numbers, we don't have any concentration, so we're not sure exactly where to start, but we know roughly. The big reference is a pH of 7. And I like to put a dotted line in a lot of my examples for that 7 pH, our neutral pH. Okay? We know the sample is hydrochloric acid because that came first. So we know we're starting somewhere acidic. Okay? I don't know exactly how far down, but I know I'm starting relatively low. Okay? If the question gave you the exact concentration, then you could figure out what pH. Now, as you start adding base, okay, that dot is at 0 volume. When you start adding sodium hydroxide, it doesn't shoot straight up. We see a relatively flat line because as you add sodium hydroxide, the acid is neutralizing it, okay, which still leaves a large amount of acid left over. There's no base as you first add sodium hydroxide. It's only when you start to use up all the acid that you see the pH shoot up, and it shoots up really rapidly. Okay? Right at a pH of 7 is the equivalence point. That is the point where the moles of acid and the moles of base added are equal to each other. The shooting up past that equivalence point is when all you're doing is dumping in base, and it's going to shoot up and level off at whatever the pH of the base is. So if we add a base that has a pH of 12, that's where it'll level off. It has nothing to do with the chemistry or the reaction. It's just that concentration. So that was pretty much all that was done last year. This year we're just going to slightly tweak it as we add in a weak species. So I'm going to jump right into the new part for a few slides. So for this slide, I'm going to do an example of like the general category of a weak acid and a strong base. In particular, I'm going to draw out what we get when we add hydrofluoric acid, or when we start with hydrofluoric acid and it's titrated with sodium hydroxide. This titrated with is kind of key to pick up. What comes first is the sample, and what comes after it is the titrant. This is important to know whether we start with a high pH or a low pH. I'll go through predicting the reaction. I've already written out all the possible chemicals we have in solution. The hydrofluoric acid, when you find that in your table, it's in the between the two gray lines. It's in the middle of your table, which tells me it's weak. When we get to the sodium hydroxide, that's ionic, so I want to split it up. Okay, and then last, I added water. Hydrofluoric acid is an acid. Sodium is neither. Hydroxide is a base, and water is potentially both. When you search your table for the strongest acid, it's the HF, and the strongest base is the OH minus. Nothing can beat that base, so you don't even have to look at your table. So our Bronsted-Lowry net reaction is hydrofluoric acid plus hydroxide ions. Okay. Reacting, okay, we use Bronsted-Lowry theory, so we have an H plus transferring. Okay. I'm writing this in green because this isn't part of the answer. This is just my thinking. Okay. The HF doesn't have an H anymore. The charge drops 1. OH minus picks up an H plus, and that gives us water. Okay. So that's the reaction. Okay. Now, we need to figure out what happens with this pH curve. We don't have an equivalence point at 7, and that's the biggest skill that I'm trying to teach you right now. I'm just going to move that pH curve up a little bit so you can still see the reaction when I'm drawing it out. So I've pre-labeled the axis, volume of titrant, pH. I like to add in that 7 right away. That should be a nice flat line. It's now perfect. Now I reread the question, and we're starting with our sample is an acid again. So I'm going to start down low. Just like before, there's no concentration, so I don't know how low. Now we get our first difference right away. When one of the chemicals is weak, we see a curve, not just a straight line coming off that dot. Okay? After we see that curve, it levels out just like before. When the HF is about to run out, we see the pH shoot straight up or almost straight up and then level off at whatever the pH of the base is. Okay. Now we don't see the second difference yet, but if I label the equivalence point, it's been shifted now. The equivalence point always shifts towards the strong species, or the pH of the strong species. The strong species, in this case, is a base. Okay. Our HF is weak. Our hydroxide is strong. So it's going to shift towards a basic pH. So that's why I've shifted it higher. Okay. Where this affects us is it changes the indicators that we're going to use. Last year in Chemistry 20, you only used indicators that worked around 7. Okay. Now they're going to be higher. Okay. So just highlighting the two new features you would have to identify in assessments. Okay. You've got that curve at the beginning and you've got a shifted equivalence point. The rest is the same skill set as last year. Now, any weak acid with a strong base is going to have this same shape. Okay? So it doesn't matter which other strong acid was put in. Now, this is one of the possible sequences. Next, I'm going to switch it around. What if we started with a different pattern? What if we started with the base first and we added an acid to it? Okay, that's going to kind of flip everything. Let's see what it looks like when everything gets flipped. Okay, as a general category, this is going to be a weak base titrated with a strong acid. Specifically, I'm going to be looking at ammonia being titrated with hydrobromic acid. I'm just going to pull that pH curve up and then give you a chance to get everything written out. Okay. Just to make sure that everybody's clear, it's always sample first, titrant second. We can do our 5 steps to predict exactly what reaction is going to occur. Ammonia is a weak base, so you leave it together when you put that on your list. Hydrobromic acid is a strong acid, so we don't see any H and Brs stuck together in the reaction. It's going to ionize 100%. Okay, into H+, which hops onto a water, and a Br-. So you see that broken up on the list, and then we always include water. Ammonia is a base, hydronium is an acid, bromide is neither, water is amphiprotic. It can act as an acid or base. Okay. Our winners are hydronium and ammonia. They're the strongest when you look up your acids in the table and find the strongest and your bases. Okay. Now, most students, once they get comfortable with this, will do a lot of the titration predicting in your head. You're never going to see water as the winner in an acid-base titration. So knowing that, the water's out. Bromide isn't an acid or base, so that would be out. So that only leaves 2 things. So that can really speed up this predicting. So we have ammonia reacting with hydronium in our Bronsted-Lowry reaction. Again, to get that visual, to make sure we've got H's in both chemicals, so to make sure we do the right transfer, we got to go acid to base. So that's the transfer. So we end up with NH with 4 H's, NH4. Aqueous, that's referred to as ammonium. Okay, ammonia is the NH3, and we get a water molecule. So let's see what changes we get because we're starting with a base now, a weak base instead of a weak acid in the previous example. Okay. So we still have volume of titrant. Make sure you get that down. Make sure you have pH as your y-axis. There's no units to pH. Something I'd be looking for is that you know whether the shift is above or below 7. So that's why the shift of the equivalence point. So that's why I put that line in. We are starting, our sample is now a base. So for the first time today, you're seeing me start up high. We have a weak species. So we're going to see it curve instead of just go out flat like we saw last year. It's going to then level out till we've used up most of the ammonia. When the ammonia is about to run out, we're going to shoot down through, go through an inflection point, and then level out at the pH of the acid. We have a weak, strong reaction, so the equivalence point will not be at 7. It's going to shift towards the strong species. The strong species is an acid, so it's going to shift to an acidic pH below 7. We know it's below 7. So just highlighting the two changes from strong titrations, you got that curvature and we've got that shift. One last big thing to mention before I kind of change focus slightly is when we see the equivalence point in the middle of a sharp drop. So I'm going to color code this part blue. When we see this in a pH curve, it tells us something about the reaction. It tells us that this reaction is happening 100%. If you just use your table, you would predict greater than 50. When we see an inflection point, it's telling us it's not just greater than 50, it's 99 or 99.9, it's essentially 100. The reaction can go both ways, but in the current setup, it is reacting quantitatively. It means that this hydronium, this strong acid, is transferring every possible H to that ammonia. It's not keeping any of them. Okay? That's what the 100% means. Okay? If it was 90%, it means 9 out of 10 H's are transferring to the ammonia. Okay? But we know that is 100% because of this inflection point. One more slide before you're going to work on 2 questions for me. So you have this acid-base table. Don't start writing any of that. That is on page 10, but I want to sort of make comments and relate this pH curve and the colors we get to that table. So the theme is choosing an indicator for titration. Now, the theory in terms of how do we decide what indicator to use is we need to use an indicator that has a color change at the endpoint, okay, that's very close to our equivalence point. Okay? They don't have to be exactly the same, okay? But we need the color change. If the color change happens at a pH of 9, we need the equivalence point to be close to 9. Okay, within a unit or so. Okay? So when I say close, I don't mean the decimal point. I'm largely referring to the number in the ones position. So I'm just going to pause for a second to make sure everybody has a sketch of this pH curve, sodium hydroxide being titrated with hydrochloric acid, and then we'll go through this in about 2 minutes. So in picking an indicator, and this is a titration like you would have seen last year, sodium hydroxide is a strong base, hydrochloric acid is a strong acid, so that's why you're seeing the equivalence point at 7. Now, in order to get the colors that are on this pH curve, we have to use our indicator table. And if somebody picked alizine yellow, that would be a really bad choice, okay? If I write out or figure out what the color change is going to be at the end point for that indicator, we first have to think what direction I guess we'll find the indicator first. It's at the very bottom of the table that I put. Now I cut a few off, so it's not at the very, very bottom of your table. And to get the correct color sequence, we have to realize that we're starting with a high pH and going low. You know, we see that we're starting at about 13 and we end up at 1-ish. I know that's not exactly 1, but it looks close. So in our table, when you're going high to low, you are going in this direction through your numbers. Okay? And that's the same direction you have to go through the colors. Okay? So we're going that way through our numbers, so we go this way through our colors. So we want to see red at a high pH, and that's what we see first in the graphic. So our color change is always the first color to the middle. So that would be red to, now what color would we get in the middle? Okay, the middle isn't the yellow, it's red and yellow. What is the combination of red and yellow? Orange. So that color change, red to orange, is too early. That would not be a good choice of indicator. Okay, if we move down to the middle one, which does work, bromothiamyl blue, here we have the color change is definitely going to be really close to the equivalence point, almost bang on. Okay. To grab these colors, again, we've got to go through the second color to the middle. So that is this line in our table. Okay. We're going high to low, so that sequence through our numbers, that sequence through our colors. So our first color is going to be blue, and our second color is not the yellow. That's if we've gone way too far. What does blue and yellow make? Oh, somebody's too quick. I just looked at the chat and the answer is already there. Green. I'll even use a green pen. Okay. And that would be the ideal indicator to use in this case. I won't go through orange 4 in as much detail, but this color change is going to be too late. Okay, if we look at what volume that we're too late, you know, we're 3-4 mils past the equivalence point. It's at blue to green with bromothiamyl blue that would tell us, okay, to stop. Okay. Okay. The red dot is the equivalence point. Okay. The end point connects to the colors, okay. And they're matching perfectly here. Okay. Orange 4, we're seeing yellow to an orange on the graphic. There's orange 4. And there's our yellow to the middle would be yellow and red, and that's orange. If you're ever not fully sure what the combination color is, you can generally figure it out in a multiple choice question, or if you look in the name of the indicator, that often gives it away. So in bromocressyl green, your two colors are yellow and blue, so if you're not sure what the middle color is, it is the combo. Okay. Now you're going to get questioned shortly. If the equivalence point has shifted up, you're going to pick an indicator that changes well above 7. Okay? If you see the equivalence point shifting down, so if the equivalence point had shifted down here, then you'd be picking something that changes color with a much lower pH than bromothiamyl blue. Okay? That green star is around 4, So we'd be looking for, you know, going in this direction for something around 4, you know, and something like methyl orange. That first number is pretty close to 4. So for that green star on the board, if that was the equivalence point, orange 4 would be a good choice. Okay. I'm going to clean out that star and that indicator because that's not this question. So these are skills I want to give you a chance to practice before we do anything else. So I'd like you to work on questions number 11 and 12 for the next 15 minutes or so, and then we'll continue with the second part of this lesson. Number 11 is just figuring out, does it shift up or does it shift down? The equivalence point. You're going to be looking at the acids and the bases with your acid-base table out, which is in the middle of your booklet, and figuring out what's strong and what's weak. To do that off the top of your head would be next to impossible. So grab your table on page 8 and 9 of your book. Okay. Question number 11 is doing that same theory, but then telling me what indicator of 3 choices would you want to use. You have to know whether it's strong acids or weak acids, strong bases or weak bases, does it shift up or down, and then which indicator would work for that pairing. In a second. Okay. So buffering regions. Okay. If students have done biology classes, buffers have probably come up a fair bit. Okay? Buffering regions are buffering solutions or solutions that resist pH. Okay? We're going to be looking for areas on a pH curve where changes in pH are resisted. Okay? And there's a few things we need to correctly identify when this occurs. Okay. So we've got 2 criteria. Okay. We have to think of what area of our pH curve resists pH change. What would that shape look like? And this is a question for students to respond to me. If we want pH to be not changing, do we want a line going up, going down, zigzagging, flat, steep? What type of slope would we have in a pH curve where pH is being resisted? So I'm getting straight line, horizontal line, flat, perfect. Okay. We need a flat region of our pH curve. So that's our first criteria. I'll stick a number 1 there, and this image goes with first criteria. But that's not enough. Just because you have a flat region doesn't mean you have resisting pH changes. You must also have a acid-base conjugate pair present. So not any acid and any base, they must be conjugates to each other. And last, I didn't type this in, they must be a weak pairing. So strong acids by themselves don't, or strong bases leads to buffering. We must have a weak acid and a weak base. Okay? Okay. We only need 1 pairing though. We often have 2 conjugates and we only need 1 of the pairs to be weak. Okay? So let's see what happens when we titrate ammonia with hydrochloric acid. We're actually going to get a buffering region out of this. So we're going to graph this out and then analyze for those 2 points, bullet 1 and bullet number 2. Now, we've already talked about ammonia and hydrochloric acid. I'm not going to go through the 5 steps to predict the reaction. Okay? When you go through the 5 steps, you find out ammonia is the strongest base and the strongest acid is hydronium. Okay? Now, we don't use hydrochloric acid. Hydrochloric acid breaks up before the reaction's even occurred. It 100% ionizes, transfers its H to water. So ammonia and hydronium, which came from the acid, is going to give us ammonium NH4, and water. Okay. That H plus transfer is from the second reactant to the first. So I have a sketch of a pH curve, volume of titrant on the x-axis, pH on the y, no units to pH. I labeled my 7 point, like I've been doing all through this lesson. Without reading it out, can somebody help me figure out whether I need to start way up high or way down low? Okay, what is the sample and what would the rough pH be, high or low of that sample? High, perfect. Yeah, so the sample is the first part is ammonia. Okay. Now that ammonia is weak, so we're going to see a curve before it flattens out and then drop and then flatten out at whatever the pH of the acid is. Okay. Just going to clean my leveling out at the end. Doesn't look flat enough, so I'm going to improve the flatness of my line. Now the only strong species is the acid, so that will cause the equivalence point to be below 7. Now a mathematical definition, this is something you're not initially tested on, but like, why am I putting the dot somewhere? What is the mathematical representation? The dot, or the equivalence point, is when our curvature changes. If you look at the top of our graph, you see the curvature up here pointing sort of to the bottom right. If you look after the equivalence point, the curvature is pointing to the bottom left at the beginning and then to the top right afterwards. So the equivalence point is where that curvature changes. Okay. So that's our pH curve. Now we're going to go back and figure out when we have a buffering region. Okay. If I look at the first criteria, 2 flat regions should jump out at you. Okay. We've got a flat region here, and then we've got this flat region at the end. Okay. But that's only criteria 1. Okay. That gives us 2 potential options. Now I've got to analyze and see what chemicals do I have at what point, and do I have a weak pairing? So let's see, what possible weak species do we have? Well, ammonia is weak, so I care when I have ammonia. Hydronium is strong, so I don't care about when I have hydronium. And I have NH4, that's also weak. And that ammonia to ammonium, that's the only possible weak pairing I'd have. I can't use the H3O plus and the water pairing because one of them's strong. So let's think at the very beginning, at 0 volume, which is my black dot, what chemicals do I have? Okay. At the very beginning of my titration, at the black dot, I've added 0 hydronium. So all I have is ammonia. So at this dot, I only have NH3. This reaction has not occurred yet. So I definitely don't have a buffering region at the black dot. It's neither flat nor do I have a pairing. Okay. Next, I'm going to move out into the middle of this buffering region and think, what's going on there? Okay. If I was bang in the middle of that buffering region, halfway between the equivalence point, okay, halfway to the equivalence point, that would be the point where I still have half of the ammonia left, and I've made half of the maximum amount of product. if I had 1 unit of ammonia at the beginning, I've only added half a unit of acid. Okay? I'm only halfway through this reaction. So there's half the reactants left over and half the products made. Okay? When we're in the middle of that buffering region, we have NH3 and we have some NH4. We have both of those chemicals. Okay? Now, it doesn't have to be 50-50. As long as we have both, we have a buffering, we have the potential for a buffering region. So we have both, it's flat, so we found our first buffering region. That would be the blue piece that I've coded, the blue line above the black. And I probably should have continued that blue line just to where it starts to roll off. If we move on to the equivalence point and think of what's going on there, it's not flat, but it's worth thinking about what's going on here. The equivalence point is when we've added an equal amount of both reactants. Okay? At the equivalence point, there's no reactants left. Okay? At the equivalence point, it's all products. So that would mean we'd have NH4, okay, but no NH3. Now I'm only writing down the red underlying chemicals that are weak. Okay, so I'm not writing down the fact there's lots of water at the equivalence point. Okay? And as we go past the equivalence point, we have all those products and we just keep dumping in more hydronium. Okay? But we never get any more NH3 again. All we have is a whole bunch of acid and a whole bunch of ammonium, sorry. So if we look at that second flat area, that is not a buffering region. I'm just sticking an X there. It's flat, but it doesn't, we don't have a weak pairing, so we don't have a buffer. So we only have one buffering region, and it is the very first one. Okay. So that pretty much wraps up what I wanted to go through in this first slide. The only last thing I'm going to add in is a reminder of what we saw before with the percent of reaction. Because we do see an equivalence point, this reaction at the moment is being driven 100% forward. It is a quantitative reaction, which just means that acid is donating all of its H's to ammonia. It's not most of them, it is all. That's what the inflection point means. Okay. If we did not see any inflection point, then the reaction will be less than 100, and we never draw those. We only draw the ones that are, in fact, 100%. Okay. So that's the first of the two big slides. One more to go. I'm going to shrink this down and then I'm going to draw a lot on it. So please have this quite large in your notes. Okay. You don't need all the individual numbers, you really just need the shape. You need the axis, we have a flattish area, an equivalence point, a flattish area, an equivalence point, and then it levels out. And make sure you record what chemicals are in this graph. And if you can just let me. Okay. So our theme with this slide is going to have a little bit of everything into it. Okay. Polyprotic species. So let's make sure we're good with that word before I get going. Poly means many, and protic is proton or H+. So these are species that can either donate or accept many H's. Okay? An example of an acid that can do this, H2SO4, sulfuric acid, is polyprotic. It can lose both of those H's. Okay? Now, how you would know both of them can be lost would be by going through your data booklet and seeing whether you see examples of both of them coming off. Okay? An example of a polyprotic base would be something like carbonate, CO3 2-. Okay? In your data booklet, you see that as a base, and then HCO3- you also see as a base. Okay? HCO3 ends up turning into H2CO3. Okay? So you have to use your data. You can't just look at a chemical. You have to use your data booklet to check. Okay? Just because it's 2- doesn't mean it picks up 2, but when you scan through the table, you see it. So that's what we mean by polyprotic, can donate or accept more than one. Okay? pH curves we've been talking about. Okay? And in this particular example, we have sodium carbonate, Na2CO3, titrated with hydrochloric acid. So I'm going to get out that first reaction that's going to occur. And I'm saying first reaction because carbonate is polyprotic. Okay? So I'm skipping the 5 steps. If you went through the 5 steps with those 2 chemicals, you would end up with hydronium as the strongest acid in the table, because hydrochloric acid we broke up, and carbonate, CO3 2-. Okay. That's going to lead to a Bronsted-Lowry reaction, making water when the acid loses an H, and hydrogen carbonate when the carbonate picks up an H. Okay. And that is going to end up being our first reaction. Okay. And we're going to see that first reaction before and after our first equivalence point. So this is the chemistry we're going to be seeing occurring in that black box. Okay, and I'm going to color code a lot of things today. So I'm going to use black for this first part. Okay. Now if we think of potential buffering regions, our possible weak combination is the 2 chemicals that have carbonate in them. They're both weak. And in this flat region, the first flat region, okay, it's not perfectly flat. I kind of use the word flat-ish now. That flat-ish region, we're before the equivalence point. So we have CO3 2-, and we've made some product, HCO3-. Okay? Because we have those 2 weak species from our first reaction, this is a buffering region. Okay? And I've identified exactly what pairing. Okay? When we get to that first equivalence point, we have run out of carbonate. Okay? At that first equivalence point, we only have hydrogen carbonate left. Now what's unique about this particular example is the fact that hydrogen carbonate is also a base. Okay? Hydrogen carbonate is capable of accepting another H. And if we keep dumping in acid from the titrant, we get a second reaction. The H3O plus makes another water, and the HCO3 picks up a second one, H2CO3. Now that reaction doesn't kick in until we've made hydrogen carbonate. So let's see when that occurred. Okay, so we can't have this reaction with that purple underlined chemical until it first is made in large quantities, and that's the equivalence point, and after it is when we see large quantities of that second chemical. So the second reaction, I'll go back to red, the red reaction kicks in during the second half of our reaction, before and after the second equivalence point. Okay? Now I had to kind of overlap those black and red boxes. Okay? What the black box spits out is the input for the red reaction, or the red box. Okay? Now in that red box, the flat region is coming from the chemicals are coming from the second reaction. Okay? And here our potential weak pairing, I've double underlined in blue again. When we're before the red box, this equivalence point, we have both of those chemicals. We've used up some of our HCO3, but not all of it, and we've made some H2CO3. We've got both of those. It's a different pairing, but we still have a pairing that's weak-weak, so we have a second buffering region. Now, you will be expected to be able to identify if there's two buffering regions, with what pairing, what weak-weak pairing is causing the buffering there. Okay. When we look at the last flat region, which I'm going to make just a thicker green, out there, all we have is a whole bunch of H2CO3. We have run out of all of our reactant pairings. Okay? We don't have both of those red reactants anymore. Okay? So all we have is a whole bunch of acid and a whole bunch of product. So that is not a buffering region. The shortcut to predicting just where are buffering regions, and you'll get that type of question on the test, all of the flat areas preceding equivalence points are buffering regions. Okay? Where I put that green X, there's no equivalence point after it, so that's not a buffering region. Okay? It has to be a flat area preceding before an equivalence point. Okay? So we have a polyprotic species, carbonate, that can accept 2 H's, and the acceptance of 2 H's we see as 2 inflection points. Now this will be the third time I'm going to label this. We see those 2 inflection points, so that tells us that both reactions are 100%. Just because a chemical can accept 2 H's doesn't mean it's going to do that 100%. Okay, but we've got data. We see 2 inflection points, so we definitely know that they were both 100%. Okay. We do see the methyl orange indicator written in. When you have 2 inflection points, which gives 2 equivalence points, you can pick either one to pick an indicator for. Okay? You generally want to probably pick the steeper inflection point. That second one at 50 mils is quite a steep drop, so that's going to give a very clear, a much more clear color change. Okay? So methyl orange was picked as a good indicator for that. I just want to decode that color change one more time to make sure everybody gets it. Okay. I quickly threw out a number line for methyl orange. I'm going to pull this data from your book. And we talked about methyl orange a little bit earlier. In question 12, it was 3.2 to 4.4 were the 2 numbers in the book. Now I want to relate the colors to those numbers. Okay? So we have 3.2 is the first number, and the first color in your book is red. So that's what we see when we're below 3.2. Okay? The second number is 4.4, and the second color is yellow. So we see that after the second number. When we're in the middle, we see both colors. So that is orange. Last would be to figure which way we're going through these colors. And this is what students most struggle with when I assess them. Students kind of always want to just go left to right. Okay? And that's not always the case. They always want to go low to high. In this case, we're starting our titration at 11 and we end up at 1. We're going high to low. So that would make the first color change yellow to orange. Okay? And I just want to write that out, and that's where we're mostly going to end things. I just have one question for you to work on. Okay? The color change doesn't involve red. You never want to get there. It's yellow to orange, okay? Y to O. And that occurs at, that yellow to orange is going to occur at 4.4. Okay? We never want to get to 3.2. We never want to get to red if we were just doing a titration and wanted to stop at that equivalence point. And that's sort of the color codes that you see written into this diagram. Yellow at the top. It's really hard to see the orange right at the black dot, at the 50 mil black dot. Okay, and then if you go past the black dot, you get the red that you don't want to see. Here, we've got a pH curve with no chemicals. So I'm asking you, what do you think the titrant might be? And what do you think the sample could be? And we'll brainstorm either an answer or possible answers that would go with this. So, can you figure out what the chemicals were that would give rise to this shape? Okay. Now I will highlight, we see two distinctive equivalence points. So that's a key piece of information. Okay. You also have exact labeling of where it starts and where it finishes, which gives you some key information. So let's see how much you can do in 2 minutes, and then we'll wrap things up. You should immediately be flipping open your data booklet, because you have to think of polyprotic species. You have to figure out whether you're looking for acids or bases, and you need your table to figure out what might be polyprotic or not. So at 1:35, we'll start piecing this together, the sample. Any thoughts of what you think the sample might be? And this one, I'm hoping you would narrow down the sample quite specifically. Sorry, I said that backwards. The titrant. The sample is what Amar gave away the category. The titrant is what? Julia says NaOH. A base. Well, the pH is going up, so that would make sense for NaOH. The other piece is your x-axis is the titrant, and it's right in your labeling of the titrant that it is NaOH. So that's actually the only answer you should have given for the titrant. We're definitely adding a base. That's why we see the pH shooting up or becoming basic throughout this titration. Okay? So we got one answer for that. Now we've got a whole bunch of potential answers. What would be some potential samples? And I'll start filling them in. This, again, there's multiple answers. I know what, well, I'll talk about what it actually is at the end, and then we'll be done. So any thoughts on that sample? HCO3. HCO3 wouldn't work by itself because there's only one H. But if you had two of them, okay, H2CO3, okay, you could lose the first H at the first equivalence point and the second, all of the second H at the second. So I'm just going to modify that answer a little bit. H2, let's look at H2SO4. There's actually a problem with that one. Most students are going to give that answer. It is H2SO4 is polyprotic, but sulfuric acid is strong. The first equivalence point, if this was sulfuric acid, would be a strong, which would be at 7. Okay? We don't see the first equivalence point at 7. Okay? The first equivalence point has to be something other than a strong species. So sulfuric acid is actually out, even though it's a really good answer. It's kind of a technical thing. H2SO3 is another answer. That one should work. Okay. Good, so we got several answers. That's a fair number of them. One more that does work is H3PO4. Okay. And that actually is the chemical that was dumped in. H3PO4 has at least 2 H's that can be lost, and that would give us those 2 equivalence points. Okay. So I'm just going to end this. So we got the right people, got the right acid, we got some good answers for the potential base, H2CO3, H2SO3, hydrogen sulfus, or sulfurous acid, sorry. And let's write out, I'm going to write out the chemistry that is occurring, knowing that we have H3PO4 is the acid, and in the first reaction, that's going to react with our base, and we're going to transfer 1 H. That's going to leave 2 H's left in our phosphate-based product and make a water. That's equation number 1, and that's going to connect to this before and after that first equivalence point. Now, this product can also lose an H. We keep dumping in more hydroxide. That's the titrant, which we can just dump more and more and more mils in. And that's going to make HPO4 minus 2 minus, and another water. Okay. And that's going to happen at our second equivalence point. Okay. So we know this one was 100%. We see an equivalence point. This second reaction was 100%. Okay. What we don't see is a third reaction. We don't see HPO4 minus reacting with hydroxide to make PO4 3 minus and a third water. Okay. This third reaction is not 100%, so I'm not going to write anything above that arrow. We could use our table to make a prediction. It is more than 50%, but it is not 100. I guess I'll write that more than 50 in. Okay, but because we don't see a third inflection point, that is, we know it's not 100. So it can be, because you see 2 inflection points doesn't mean the acid was diprotic. 2 inflection points means it's at least diprotic, but it could be more. Okay? If you see 1 inflection point, it could have 2 H's, but the second one just doesn't come off. Okay, so we end in with, we have a little bit of ambiguity. Okay. Normally you do a lab and I'd have you do some analysis, and when you're doing labs with pH curves, you have to use words like at least. 2 inflection points, there's at least 2 H's. There's not 2, there's at least 2. There could be a third that you haven't seen. So that wraps up today's lesson. Some questions to go through to wrap up the buffering region section. This is a section the students tend, with some practice, you should do fairly well on. There's no calculations. You'll get a couple questions on this on your test or quiz.